I had a couple questions, so let me find the questions that I had.
Our first strategy is to use Monte Carlo learning.
No, not this guy.
We're not. We can't see your.
Yeah, it's not for this. Oh, it's not the same.
Can you share your screen to the remote?
Right. I'm just trying to find the lecture that I got stuck at.
Our second strategy will be to develop.
First of all, to anyone online, do you have any questions? Like, have you stuck at some point where you wanted to double check what's happening?
Mm, not particularly, no. I think as you go across, if anything comes to mind, we'll definitely shout out a question.
All right. Willie, Brian.
Yeah, I think the same here. I just have to, I mean, I haven't reviewed this stuff since last week. I just reviewed it this afternoon before the meetup. So I mean, everything seems okay. I think there's a few little bits here and there. I don't, not exactly sure, but probably nothing that I couldn't just, you know, get the details my own, just a quick look up. So nothing stands out anyways.
Okay.
Yeah.
I think I'm just maybe a little confused about some of like the limitations with experience replay and some of these models, like when you define the states and the actions and rewards. But I'm sure that we'll figure that out when we go to implement it anyway.
You were confused with
Some of the limitations of experience replay.
limitations with the
Experience replay.
experience. Okay, so there were two things, right? Experience replay, and the second one was the fixing the weights. Yeah, those two were confusing to me as well. But before we go to that part, do you have any questions with this part?
To be totally honest, I was just in the kitchen cooking some spaghetti, so I'm not sure what you guys were talking about right now.
So we're trying to go over the deep key learning algorithm, make sure we understand the whole logic, what's happening. First, do you have questions about offline policy and online policy? How Q learning is different from SARSA? I think that one is pretty clear, right?
Yeah, I mean, I feel like I'm still working on getting this intuition down because it's almost feeling a little uncomfortable to me to imagine feeding in these like raw pixels and your output layer just being your controller, inputs or whatever. But I think once I play with it and implement it, it'll make probably a little more sense. Just feeling a little uncomfortable still, to be honest.
Okay, I think that's fine. Yeah, I don't think.
Actually, for me, it's not so much questions, just, well, I guess questions, but the thing I noticed is just to try and keep track of everything, especially since they added all the tips and tricks, is like there's just even more variables, there's just more functions, and it's like mostly you gotta, I guess, keep notes, keep track of everything, because there's just so many moving parts here, and that you have to try and keep in your head as well, because you're adding functions on top of functions with the with the policy. So I think that's it, just remembering everything.
I mean, I don't know. Their example with Atari kind of makes sense to me, but then when I try to imagine incorporating it into other applications besides just a simple game, I kind of just end up like feeling, I guess the word is like insurmountable. I don't know how to even approach that problem.
I think, well, for other cases, DQing is not necessarily the solution. I think that's the short answer, because there are just so many variants out there.
Yeah, I mean, that's where I guess I'm saying where I'm kind of confused with how you define some stuff. I think like what I saw in Deep Q Learning, and I'm confused with is like they're just feeding in the raw pixels of the Atari game, right? And then they're letting that output into different decisions and then experience replay. And that seems great and all, but I'm just wondering like what the limitation is of what you can actually feed in with just pixels and still be able to take actions on.
So, what are the limitations on what you can fit in and have the output?
Yeah, exactly. Like it's in that game, right? You know that you just have these like controller buttons like left, right, and like sideways and diagonal, and the input is just the same pretty much image, but with the paddle at the bottom being at different locations left to right, and with different variations or combinations of the little Atari bricks being there or being disappeared because they've been knocked away. So it's like kind of easy for me to imagine in that situation, but in other things I couldn't really. I'm not visualizing it all. So maybe Ziyang's right. It's just not really applicable elsewhere, and it's mostly just for a few applications. I'm not sure yet.
So the application that I can think of, the deep key learning would be applicable if your input state space is really big. That's what I'm thinking. It doesn't have to be images, but
So you broke up. If your input space is, pardon me.
input state space is huge. So that's the whole idea, right? Because if your input state space is small, then you can just use the table-based key learning. Just put everything into table and learn based on that. Now, if your input state space is really, really huge, as the case with the AlphaGo or as the case with the video games, then you have to find a way to kind of condense it. So maybe, and that's essentially the idea for neural networks, right? They can map complex functions. They can map complex inputs to outputs, and they find features for you.
So I guess it is like a universal functional approximator too, but it's kind of one with constraints and I don't know if I want to use the word bound, but you're trying to, for I guess the set amount of actions maximize reward, right? So I guess it really is just like a functional approximator in that sense.
Functional approximator.
Yeah, that part, the Q part is the functional approximator. Yes.
Okay, so just to make sure we understand, to me, I was thinking to this network part, right? Neural network part as like more of a sensors, right?
What?
So more of a sensors. So you get some input into this network, into your key learning network, and but in this case, it does both. It does first sensing, which essentially like getting the input data, right? So it gets the input frames, and then it learns how to behave. So
that reminds me of like Kalman filtering almost.
Yeah, it would be a bit easier if you could. What?
No.
Yeah, it would be a bit easier if you had like two parts, right? If you had this thing, one part is you have this complex world, and you break it down to a simple representation, and you have another network that learns based on that representation. That would make it a little bit easier for you to, I guess, understand it intuitively. But in this case, you have both of them at the same time. Like you have the network that both gets the input from the world, finds the features, and learns at the same time. So it does everything here. Now, so in regular neural networks, if we look at the networks as let's say convolutional neural networks, the ones that just look at the image and find interesting features and pass it on further, then you just do backpropagation with the gradient descent, right? And those weights are essentially, okay, what pixels should I care about? What value should I care about? But in this case, you adjust weights based on the reinforcement learning algorithm. So instead of just saying, okay, what pixels should I care about? You also say what pixels and action should I care about? Am I too far off, or is it something close?
I don't think so. This is pretty much the same with like seeing and classifying CNN.
It does.
It's just output is action, input is pixels.
Yeah, but you don't train it. You don't.
Sorry, output is not
Output
output.
is
It's
Q
a values.
Yeah.
Values. Yeah.
But you see, like in regular network, when we find errors, we find them based on label data, right?
But in here,
In this case, we don't have labeled
it's
data.
not a label.
No, we don't have labeled
No,
data.
it's not labeled.
in this case,
I think that's kind of like the function of the experience replay, isn't it? To be able to kind of like get some, I don't want to say label, but to, through trial and error, kind of work its way into the best action, considering it doesn't have any, underlying ground truth that we are feeding in at the time. I don't know. I kind of understanding it like you, to be honest.
These are here's the label. The label is the reward that you get. Okay, it's online learning. The label, okay, that the narrow part of learning Q is still labeled training, but you just get labeled through a reward plus the future, like a discounted reward from another network. But essentially, when you actually update ingredients, still gradient descent, and the way you find those differences is still kind of labeled. Narrowly speaking.
If you want to call it target or label, then yeah,
okay,
yes, it's labeled.
Yeah. So okay.
I actually have a question, just a quick question I want to ask. For the states, I want to confirm that for like the example in the videos, it was a single state is 84 by 84 by 4.
Yes.
Correct.
That's a single. Okay. Yeah. These are big. Okay.
And the reason we do 4 because we want to know the temporal difference as well. Right?
Yep.
Okay. So
which video?
we have videos we posted on our
Yeah, I know, but which one was it? 84?
I think it was here, like this input.
Yeah, I can look.
Yeah, that one is 205 by 180, I think, or 160. But they made it into a square and they made it gray.
Oh, right.
Yeah. So
video number 6.
Video number 6. Okay.
I guess if we go back just 1 minute, I guess I am a little bit still confused about in like deep Q learning, like if it is what you were kind of saying, where the weights are now like attributed to both the state and like that specific like layer neuron that you're looking at, or how it kind of works, since like regular backpropagation makes sense to me, but here it is kind of confusing.
This is still you still apply regular backpropagation.
All right, so let's.
But you only perform one gradient descent at a time. Yeah. Online learning. Yeah. You don't totally converge to optimal.
All right, so is someone's mic on? No. So this is the temporal difference learning, right?
Mm.
So this is how we update our values. Okay, let's just look straight to our Q function.
Are you guys meaning to share a screen? Because I can't see anything.
Oh, wait a second. You don't see our screen?
Yeah, I was just meaning to ask that.
Okay, sorry. Oh yeah, I don't share screen. Oof. Application window. What is this window? No. Can you see it?
Yep.
Okay, so essentially, we are right now working on this deep Q learning document that you can find on our drives. Do you have access to these drives?
Yeah, it's the one posted on Slack, right?
Yes.
Mhm.
All right, cool. So, do you all understand this formula?
I don't think they can see what you're pointing. Oh yeah,
I think they
never
can.
mind.
Can you?
Okay.
All right. Do you all understand this formula?
No, let's speak through this formula, please.
Okay. So the first one is the value update. Those are both are exactly the same. This one is weight update for value function, right? So if you look at the very first video,
I forgot the content.
give me just a second. Now let me pull this guy up. So this is what they were saying, right? You have
I mean, I'm pretty sure I've seen that same same two equations somewhere with labeled like terms in them. So I don't know. can't find it right now. I'm looking.
Now, this one is a classical key-learning. So let's first look at this, right? So you have very complex state space, right? And then you want to learn some value function. So given a state, find the best policy. I mean, yeah, given a state, find the value for that state, essentially. I think this is the value function, right? Now, if your state is huge, then what you do is, by the way, XS, this one I forget. I don't think we covered this. This is the feature transfer. What was that feature transformation?
It's the phi, right? Phi.
Is it phi?
Yeah, that's the features of your students.
Okay.
Oh, okay. So given X, given state, you convert it into that feature transformation, and then you feed it into a network, and that network's find you the value.
What is the feature transformation? Is it just like a matrix or a vector? Is it what exactly is it?
Yeah, good question.
So
I'm thinking it's kind of it's like a picture being like 10 by 10 pixels getting turned into one vector of 100, right? Something like
Oh, okay,
that.
so that is flattening it into one
Yeah,
vector.
that's one of the ways of doing it. Yeah.
Say it again, flattening of what?
Wait, what?
Well, I don't know if you want to call flattening, but just taking
Yeah.
whatever dimensions it is and making it into a one-dimensional vector.
Yeah, like how you transform a picture, a 5 by 5 pixel picture, for example, let's say, into a 25 one column vector, and then we work on that. That's one example of transformation, right?
I don't think that.
Yeah, I thought we'd do more than that.
I thought that was when you take 4 frames and make into one,
What?
right?
There's a whole lot of like. I mean,
Yeah, it's just one of the examples. These are many different. It's just transforming the state into a form that we can work with.
So it's a straight reshaping in a sense. So there's no other transformation going on.
I could be more than that.
Yeah, I don't think there is an actual transformation besides just the dimensionality, because it looks like that's right before it feeds into the actual network. So I think that's just so it's easier for the linear algebra to be done.
Oh, why do you bother to
Why confuse us? Yeah.
All right. So what is the feature?
In this paper, they have a few games, but all the.
I think in the
features are
paper it's
also-
called phi.
Yeah, but I mean, they're not explaining. What do they explain properly?
Yeah, I was trying to look for the definition of phi, but I couldn't. This paper is too
I
bad.
don't remember.
This is the convolution.
I think phi is phi is some kind of transformation, and you see the result of phi into Q.
Yes. Where is the file? Which page is that?
In the algorithm 1 in the appendix, page I don't know which page. 7, yeah. But I can't find the define.
Yeah.
Oh, pre-process.
Mhm.
Yeah, right over there.
Here.
You got like 3 lines down, and pre-process sequence, and that's all it says. You're too far.
Too far?
No, you're 2 lines below the one you highlighted.
Oh,
This one.
okay,
That's
okay.
it, and that's all. That's the
So
first
can
time
you scroll up? Can you scroll up? To figure 1. Scroll up. Here's a figure 1.
Oh yeah, so
There's a pre-processing part in the methods.
Yeah,
So
figure 1. More. So on the that one. Figure 1. Look at the description of figure 1. it says the details about the input to the neural network consists of 84 by 84 by 4 image produced by the pre-processing map.
Go to, what is this page?
Is it just like,
6. Go to page
is
6.
it just standard like normalization
Go
and
to
stuff?
the top of page 6. That's your answer.
Yeah, I think just standard normalization. Sorry, wait, what?
Page
Go
6.
to the top of page 6.
Yeah. I think just maybe
Yeah, that's
standard
pre-processing.
normalization and stuff.
Apply pre-processing.
Reducing the input dimensionality.
Encode a single frame and take the maximum value. Okay. Yeah,
Oh, they
do
turn
something.
it into grayscale first, right?
they do other stuff as well. It's not just changing the dimension.
Grayscale to 84 by 84. What?
Everyone said that we read the paper.
I never said I read the paper. Just
I honestly said no.
Okay. Working directory. Okay, so in our case, access.
So wait, they are making it just grayscale? Because I guess that kind of makes sense if that's the case. I guess the color pixels don't really contain any meaningful information to learn, right?
Yes.
I think the reasoning is that if humans can do reasonably well in grayscale image, so can a machine. It's because it contains enough information, we don't use any details.
I'm sorry, Zhang, it's almost impossible to hear you. Maybe you're really far from the mic.
Talk louder.
Oh,
Listen.
I actually, okay, I don't know if they converted to grayscale.
They did.
Let's just read it.
Oh.
Yeah, Y channel, also known as luminance, from the RGB frame, and rescale to 84 by 84.
I guess if it was like a game though, where color encoded for some type of like different reward, like maybe I don't know, like Candy Crush or some bullshit, where maybe I don't know if it's actually Candy Crush, but you know, maybe that one little block being blue versus red means there's a bigger reward. I guess in that case, you couldn't really throw away the color pixel.
Yeah, I don't think they ever converted that to grayscale. I was wrong, my bad. But they do say like 108 color palette was too much, and they scale that down.
I think they will scale down the number of pixels, no?
Okay, I just need
Because they're
yeah,
saying
probably.
the phi is a preprocessing map that creates an 84 by 84 by 4 image that they're taking. They still keep it for
Yes.
frames, right?
4 frames is to see the temporal difference.
Yeah.
Yeah.
So then they're not taking out those 4 frames, they're actually keeping them, but they're reducing them number of pixels.
Mm-hmm. There's some kind of flickering thing like anyway.
Look at the key. You need to pick up Harriet. Yeah.
Sorry, what?
You need to pick up Harriet. Look at the key. I know, like, well, it's Harriet.
We should do a big about it.
15 minutes.
I know.
Yeah.
But Harriet let us know ahead of time that she's a bit late.
Oh, she did? Okay, then. Fine.
So does anyone know why it's called temporal difference learning? Because from how I understand it, it's just like bootstrapping from that current estimate and they're resampling and trying to optimize based on that. So I'm not really like, temporal to me. Usually, I would think time difference. Hearing those words.
Okay, temporal. My understanding comes from the fact that you only periodically update your queue because you're basically calculating difference by calculating from a previous version of the network, and you periodically update it. I think that's when they.
Okay, that makes sense. That makes sense.
I think if you look at Richard Sutton's book, maybe it's the video as well. There's actually, I think there's this TD0 algorithm he described. I remember correctly. So his book is really good because it actually like show you a whole bunch of different algorithm that progresses all the way to Q-learning. So
I think I'm only a little confused because in his book, the only chapter I read was the one on actual like dopamine and neurobiology, and that was maybe like chapter 20 something. And he was already mentioning, he was mentioning temporal difference learning there and like it's biological.
Start reading. They call it TD0.
Even in these videos, they were leading up to Q-learning, so they haven't. So Q-learning is a method that progressed out of dynamic programming and TD learning. And in the videos, they were going over how these two are put together to go.
My understanding was different for temporal difference learning of.
Can you speak louder?
Oh, okay. So from where you've got actions that take place over time, your current reward is equal to the current reward, whatever that is, plus the future rewards. Yeah. And let's say that there's no rewards right now at the moment. So the current reward is just discounted future reward, right? Now the Q values that come out of the network to begin with are more or less random. Like let's just say they're randomly initialized. So your next steps value from the Q function is going to be just straight out wrong based on the current one. Just again, assuming that there's no reward at all going on. So the purpose, I think, of temporal learning is to just bit by bit kind of even the system out and make sure that the next steps, like the future time steps Q value is more or less equivalent to the current one with the discounting factor, unless there's the R, in which case it has to be like adjusted by that value. So does that kind of make sense?
Yes,
like
I think you're right. You're right.
Yeah,
I was wrong.
It's weird to understand. It's hard to explain, but it's kind of like saying that my current happiness is based on my future happiness. What if I know what my future happiness is based on? Well, that's based on my future happiness of that. So it's like it's a big cycle of like it doesn't work. But if you do it enough times, in enough different spaces, eventually it'll even out to something that makes sense over time.
So I guess is that why like the experience replay kind of works so well, where it kind of is just learning like little segments, but in the end, when you actually have finished training the model and you go to test it, it somehow does really well, even though you just start from the beginning of the game now and you're not actually like starting in these little random, segments of these blocks being there and not these ones, because that was that little chunk of experience replay. Or am I misunderstanding this?
No, that's the way I understood it too. I liken it to like if you've got a blanket that's like on a bed that's messed up and you flatten it out bit by bit, and eventually it becomes like a smooth blanket, but you're not like you're not just starting from one corner, you're just kind of like doing lots and lots of different places, and eventually it just all smooths out. And that
makes sense to me.
Can we take a look at you said the video has a TD0 tempo before it goes to Q-learning?
Yeah.
Because I remember seeing it. Can we revisit that real quick? TD. Someone refresh my memory. Yeah.
Is it TD0?
I'm not sure.
It's just TD learning.
Our second strategy will be to develop a temporal difference technique with function approximation. Compare the incremental update step between Monte Carlo learning, where we use the actual return obtained through the episode, with the temporal difference case, where we use an estimated return. This is called the TD target. And in the simplest case, TD0, we use the next reward plus the discounted value of the next state. In a similar manner as before, we can use this TD target in place of our unknown true value function. This gives us something concrete to work with. No more oracles or other imaginary creatures. Note that we had to adapt the value function to use our function approximator we had. This entire difference is called the TD error and denoted by delta T. We can extend the same idea to action value functions as well. All right, we're ready to build an algorithm around this update rule. We'll use a TD0 target and focus on the control problem again. As you may recall, this is essentially the SARSA algorithm. We begin by initializing our parameters W arbitrarily. Our policy pi is implicitly defined as an epsilon greedy choice over our approximate action value function Q hat. Then we start interacting with the environment. For each episode, we begin with some initial state S obtained from the environment. We continue interacting till we reach a terminal state. At each time step, we choose an action A to perform and observe the reward R and next state S prime. Now we choose another action A prime, this time from state S prime, according to our epsilon greedy policy pi. This gives us all we need for the SARSA update, S, A, R, S prime, A prime. We plug these into our gradient descent update rule and adjust our weights accordingly. Finally, we simply roll over S prime to be the new S, A prime to be the new A, and repeat. This formulation is useful for episodic tasks, where each episode is guaranteed to terminate. It can be adapted to continuing tasks by eliminating the distinct boundary between episodes and treating the sequence of interactions as one long unending episode. SARSA is an on-policy algorithm, which means that we are updating the same policy that we are following to carry out actions. This usually works very well and converges pretty quickly because you are using the most updated policy to take each decision. But this also has some drawbacks, namely that the policy being learned and the one being followed are intimately tied to each other. What if we wanted to follow one policy, say one that is more exploratory, while learning the more optimal policy? That's where we need off-policy algorithms.
So what exactly is the alpha? Is that like a learning rate parameter, or what is that right before the bracket? Sorry to interrupt.
I think it's learning rate.
It is.
So to recap, so it's basic. The limitation of the SARSA is that effectively it could get stuck into a situation where it just doesn't explore as much. So that is why you need the learning or experience replay. So that's not enough. Then you add something else. I forgot. Does that make sense?
What?
Why? So you might only end up exploring a certain subset of states and actions, and you might not actually explore the whole entire space broadly enough. That's the limitation of SARSA, right?
It's a online. That's the main challenge. So essentially, is you learning as you act.
I think you're both saying the same thing, by the way. Yeah.
Oh, saying
Yes.
Okay.
Exactly.
I think that this might be a little bit different though. I think that this one you can still do an exploration phase. Like it doesn't have to choose the most greedy policy. It can kind of explore. But one of the fallbacks to this one is that you've got a really long system of steps. It's updating its policy as it goes. So it's not necessarily learning the strategy that works well overall. It's learning you just have to change its mind on how to interact, which can cause like unanticipated effects because you're not training on that one strategy. It's like it may be bouncing around as it goes.
Why is the gamma increasing order in the actual return equation?
Gamma? Where is that? This?
Yeah, it's increasing exponents. If you take a look, it doesn't even appear in the first term.
Yeah, if it's the discounting, it's because it's less than 1. So as the exponent goes up, it gets smaller and smaller. So you're just shrinking the value of future states.
Oh, so it's almost like it's the Taylor expansion of E. They're trying to do like an exponential decaying process.
Yeah, it's getting smaller. Yeah, so yeah.
So
I'm going to assume at some point they cut it off too, so you're only looking ahead so many steps in your valuation, I guess. Well, especially if it's continuous, it has to, at some point in time, say, okay, we're done calculating our valuation.
it's gone factor, right? Okay.
Yeah, no, that makes a lot of sense because if you're going to be calculating like 3 time steps into the future or whatever 3 states, it's going to have to become discounted looking from the present into the future. You're not going to be able to weigh that as heavily because you just don't know.
Yeah. So just to quickly recap, Yervant. I just want to make sure I pronounce it correctly. Sorry. So you said the reason we use full frames is that's what you were talking about, right? With the blanket, or no?
No. That was a temporal. No, blanket was more about how to make sure that
Yeah, feel
Q
free to
values
draw.
function.
So if you wanna draw, just make sure you join the Hangout and put your camera on so we all can see.
Okay. Yeah, I'm a little far.
It's on RL workshop. There's a link here. This one. No, this one.
Cool. Okay, so feedback. So should I just talk to that one?
You can mute. Okay, I'm gonna mute myself.
You can mute yourself and just to open the camera.
I'm gonna.
Okay. Okay. Cool. The current value. So Q, unfortunately, is. Should I share or something? I don't know.
You are sure, yeah.
Okay, cool. Q as a function, because it's a neural network, unfortunately, is basically random to begin with. So if you say, like, this is, let's say this is just a set of states that I'm just going through, this, you know, like this time 1, this time 2, this time 3. The Q value for this could be like 1,000. This one could be 0.5. You have no idea what it's going to be. But in reality, assuming that there's no reward here, just for the sake of simplicity, there's none of these have a reward. This and this should be more or less the same. This should be 999. Sorry, the other way around, not that way. This should be 999 if this one's 1,000, right? Because it's kind of like.
Even for the same.
I mean, if
for the
you're
same input.
For the same. No, so like this is the state. This is state 1 at time t equals 1. The state at time t equals 2.
The number above is the value.
Yes, and this is equal to, like, the difference between V and Q is basically one has action, the other one doesn't. Right?
Yeah, sure.
Yeah, so let's say V to keep it simple, right? V is equal to, but because it's a neural network and it's all randomized to begin with, this could be 1,000, this could be 0.5, this could be 2 billion, who knows, right? It's just, there's no sense to it. It's all random, right? Yes?
I have something to put that. So what do you mean state at time t equals 2 is random? Because at time t equals 1 or 0 is the initial state. That's where you would have your rates being random. And the update, as you traverse in time, is going to take into account the rewards you're going to get.
Yes.
And then the way to update is
yes.
no longer random.
What I'm saying is what you think it is. It's almost like this is like you. If this was a human, it would be like a baby who has no sense of what is valuable and what is not. It's all random noise coming in. Because a neural network, basically the weights are randomized to begin with. The output given a set of inputs is not really predictable unless you randomize it, set them all to 0 or something like that, right? So to begin with, we don't know what it's going to be, what the output is going to be. What we want is for these guys, like the value coming up for this state input and this state input, these are all inputs, right? States are inputs, to be more or less the same. Again, assuming that there's no reward at any of these states, right? We want them to be close to each other because moving from state 1 to state 2, assuming that this is something that, like, they're close to each other, like in terms of states, and if there's no reward in there, you should have more or less the same value. That's what the function does, right?
They kind of have to be the same.
Exactly, except with a slight difference because of the discount, right? But more or less exactly the same. Because the discount.
Because if you have no reward, if you start with 0, then you're going to stay at 0 as you change over time.
Oh, well, no, because it isn't. So somewhere down here, we assume that there is a reward. And let's say the reward here is just 100 or something like that, right? So this is going to be like 99, 98, 97. So we know that it's not going to be 0.
But we're only talking about single time steps.
Yes.
Not a full sequence.
Yes, exactly.
So this isn't like Monte Carlo where you have a full episode.
Yes, but what I mean is the result, the output, at the very end, once everything's perfectly aligned, once we've got all our results, there should be, like, if this is 100 and like S is equal to state, let's say 100, just to keep it simple, then S is equal to 99, assuming that you can have an action. It should be very close, right? But it isn't. Right now, this is all garbage coming out. So what we want to do is take this, what if you were to imagine like the V values coming out of like the inputs, it's like something like this, right? It's like all over the place. So what you want is to make sure that it's actually smoothed out. So if this is 100, this is equal to 99, this is equal to 98, assuming that there's no reward in any of these. If there is a reward here, then just adjust it based on this. If there was like a reward of 5 here, then it would be 98 plus 5, but then this will be 103, 102, right? So like there's some pattern to this. So the problem with doing this online is when you're doing the loss function, you have no idea what the next step is going to be because your loss is equal to, what was it again, like reward plus Q of the next step.
Gamma times Q.
You see, yeah, sorry, gamma minus Q of this step, if I remember correctly, right? Yeah. But if you don't know this value, how could you possibly determine loss? You can't. If you don't know, you could say, well, this is going to be the one, you know, like if this is Q, gamma QS plus 1 is equal to S plus 2 gamma, right? But then you don't know the next value either. So it's just a big cyclical vicious cycle. You have no idea where to start. But the way that temporal difference works is it accepts that. It says, okay, cool, we're not going to know for sure, but let's assume it was right and just start adjusting it bit by bit over time. Because, so let's say, what? I'll stop and just make some questions.
Even that formula has some like correction power because it has the Q, the wildly random thing is discounted by gamma.
Yes.
You plus that with R and it's minus your previous random thing. I can imagine like over time it can adjust itself.
Exactly. Exactly. Yeah, that's exactly the point. Just like again, the metaphor of the blanket is bad, but like let's say that these two should be close to each other, it should be smoothed out. Well, as I move this one down, then this also starts to go down a bit. So it's kind of like starting to flatten out. Like if I press down one part of the blanket, the parts around it also start to flatten out. And it's kind of like if you do that enough places, then the whole thing becomes more smooth. And that's what you're going for. Remember, this is smooth, 100, 99, 98, it's smooth as opposed to being random. Now, of course, that's the simple case. You have to also count rewards if there's a reward in here, but that's already taken care of with this part of the loss function. And so you're good. Like it's the same concept, you just add an extra little bit of data in there, like a little bit. Did that help, or am I don't know if I'm.
Yeah, but which part smooths the thing?
So let's think of it this way. Let's say you have two states that are.
Maybe you can erase it.
Oh, sure. Let's say you have two states that are near each other. Where's the eraser? Oh, here it is. So you have two states that are near each other. This one was 100 and this one was 50, and that's just straight up wrong, right? Because it's too far away from each other, just for simplicity's sake, right? Now, you accept, this loss function accepts that they're probably wrong, but it says the loss between these is, again, assuming no reward, the loss is 50, right? Because it's 100, current state, 50, and then plus the gamma, so if this is 50, it'll be 51 is the loss, right? So,
sorry, what? It should be less.
Yeah, did I do that math wrong? Sorry, I'm just trying to figure out.
Gamma is less than 0. Well,
yeah,
less than 1.
So it's 49? Yeah, sorry, 49, right? So the loss is 49. So that's a big loss. And so it back propagates that in a way to make these go closer to each other. So this will probably go to something like 95, and this will probably go to something like 55. So these are getting closer to each other. Now, it's not perfect yet, but then you do that somewhere else, and they get closer to each other. And then you do that somewhere else, and they get closer to each other. And eventually, you have something that's more, that where the loss basically goes to 0, hopefully, in all cases, because you've adjusted enough places over time, and you do it over and over and again. Because like this one went to 55, 95, and 55, but then this one was wrong. Let's say this one started off as 200, but then this guy goes, oh no, that's wrong. So this has to go to 65. And this one goes to 180. See how they're getting closer to one another, etc. And then if you do this enough times, then the whole thing becomes the function that it should be. Is this helping?
Yeah, so what you mean is the smoothing happens as you go, as you visit, right? As you pass through it.
Yes.
So it's not like you smooth one state and everything around it. You just one at a time.
Well, it does actually do that a little bit too. Well, no, you don't do everything around it, but it will automatically, because of the way neural networks work, it will actually do that, just like the blanket. You can't just push one point down, parts around it are also affected, but that's just a nice byproduct. It's not important that happens.
So count through and can we stick to the example, like
Sure.
what happened? I just want to calculate at the beginning L equals to R. So here say R is 0. Right?
Yeah, R is 0 in this case.
Plus what is it? 50 minus 1. Oh, sorry.
49.
49 minus 100.
Yeah.
So what? How big is the loss? R plus 49 minus 100.
So it's
49
negative,
minus 100 is minus 51.
Yeah, negative 51. So that's big loss.
So if we do this correctly, then the next step is it becomes 65.
Well, I guess some numbers here. Yeah.
I just want to check.
Yes.
Correct. 65
So,
then discount.
No, so I did 55 here.
So if you discount that, it's like say 54. So the next
sure.
54 minus 95. It is decreasing. 54 minus 95.
Oh, I see. Oh, okay. Yeah. Sure. So this one will be 55. This one will be 95. Yes. So that is.
So is the gap closing?
40, I think. Negative 40.
Okay.
Right?
So the gap is closing.
Yeah. And it should be, obviously. Otherwise, you're doing it wrong.
Okay.
And you don't want to jump right to it. You also want to put alpha in there, so it's like slowly adjusting.
Yes. That's why I didn't say like this goes to 50, that 75 and 75. It's going to be slow, because otherwise you're just going to go like it's going to be unstable.
Okay. So how do you use the loss value? Where do we plug it in?
The loss is how you back propagation through a neural network. The loss basically tells you how badly you should change it.
Computer gradient.
Yeah.
Those formulas.
Right. The backprop inherently has the effect of closing that gap.
Precisely.
I see. So what you're saying is the other areas are being affected because this during the backpropagation neural networks actually accounts for the neighbors.
Well, this is kind of a downside actually of neural networks where you can't just change. You can't change S is equal. So ST is equal to 2. S is equal to T equal to 2. The Q value of that without also changing things around it, because that's just how neural networks work. They're too fuzzy. You can't just say at this point with this exact data, I'm going to change it, but nothing else changes. That's not how neural networks work.
I see. So neural networks actually do the blanket side where you put
Yeah,
them down
yeah. Which is actually technically a problem, but that's why they do batch copying.
Yeah, that's my next question.
That's fine.
Why is this a problem? The SARSA is not enough, right? So
there's two problems that are being solved. One of them is that SARSA is too.
Sorry, this is SARSA, right?
Well, no.
Sorry.
Well, it depends on how you implement this. Now, we're getting into a different topic. Do you want to? Because I can stop now.
Sorry.
Yeah, I can stop instead of keeping on talking. Well, I don't.
Oh, you're done. Okay.
Yeah. Well, I don't know. What do you want to talk about now? I don't want to be just the one,
I think
monopolizing everything.
For me, I can accept that. That intuitively that kind of makes sense. But then I think that's not what SARSA is doing effectively.
SARSA is doing based on one step.
We have not distinguished between whether this is SARSA or whether this is the Q learning method. Just say in general if this is correct. How with the intuition.
Then my question is basically what's the problem with SARSA and how do we transition to Q learning? That's my question.
Let's see if we can get the function out.
So, as I understood it, in SARSA, we're calling one policy all the time to calculate Q value.
Okay.
And this is not necessarily the best way to do it because we
Sorry about that.
Thanks. Go ahead, sir. Go ahead.
best explained in the video, but as we were talking about last time, we have both an offline policy and possibility, or sorry, an off policy and on-policy technique. The off policy technique is the Q learning, where they use a different policy to update the Q value. That's the greedy policy. Like that's the picking the best action for this Q value.
Okay.
Versus off policy could be like epsilon greedy or some other policy. Like you could randomly choose your best Q value. Or not your best Q value, but the Q value to set to.
The reason. is because
I guess
what's
Q
your reason?
learning learns faster.
But
So
why?
you can learn with the
Because now
Sarsa.
you're following an optimal setting of Q value in your table now, right?
You're following optimal set of Q value.
So if you look at the difference between Q learning in terms of that formula, I'm probably
What
gonna
do you
open up
want?
yours. I can open up in front.
What do you want? This one?
Yeah, I guess go up to the or
Formula?
go down to the algorithm.
Isn't this complicating because it's DQN?
Actually, yeah, maybe it's not the best one to look at. I'm looking at the one in the book.
So did Sarsa come first? Because the Q learning equation, it kind of looks like similar, but with a couple extra terms added.
Yes, I think it came first. So first it was Monte Carlo, I guess, and then there was Sarsa, and then we switched to TD Lambda maybe, and then Q learning. Maybe those.
So when they were doing just Monte Carlo, they were pretty much at that point just like that's just like brute force, no? I don't know.
So the way it had historically progressed was that there were two techniques, Monte Carlo, which is this idea of sampling over time, and dynamic programming, which we didn't really get into, but these are combined to develop TD learning. Then there is this extra bit, which I would probably talk about right now, which is the reason that they are developing Q learning.
Mm-hmm. Okay. So before we
Sarsa is one form of TD learning.
Okay. So before we go too crazy there, right?
Like
let's make sure we understand this part. We all understood this part, right? We all good.
Yep.
We need to look an example, like specific code.
Okay, I'm sharing my Sutton. Do you know which chapter the Sutton book is talking about?
Which one?
The Sutton.
Yeah,
Sutton
in that what? You're looking for?
I can't find. Okay. I remember there's a progression that they start off with TD0 and then go.
If you just look at the names of the chapters, you understand what order they're going in.
On policy prediction approximation, on policy control with approximation, off policy method with approximation.
No. I'm not even going to that depth. I'm just saying, like, if you look at the names of the chapters, they first start Monte Carlo and this and that. Probably the video.
Oh, sorry, it's in the tabular. Okay, Monte Carlo methods. I was looking at part 2, and then temporal difference learning. Can you see my screen?
Give me a sec.
So you have Monte Carlo, and then temporal difference, and then it goes to TD.
Mm-hmm.
So this is what we talked about just now.
Yeah, that's pretty much what
when you see what is part of what, like we see it all as exactly temporal difference learning. The Q learning is temporal difference learning.
That's right.
Chapter, right?
Yeah, it all falls under that umbrella.
Mm-hmm. And then the limitation of TD is what? Is TD0 is what? Advantage of optimality. And then Sarsa. We turn now into TD prediction methods. But okay, so from TD to Sarsa.
When you say TD0, understand that we only talk about 0 because we've only looked at 0. There's a more complicated, basically format of this, where they have lambda, but we don't need to get into that basically.
Yeah. Okay.
Yeah.
All right. So what are we trying to figure out, Mike? Could you formulate a question that we're answering?
Okay. I'm trying to figure out. So TD0 is something I think is the simplest thing. It intuitively makes sense to me. And then the reason I think they introduced Sarsa is because there's some limitation with TD0, and that's why they came up with Sarsa.
It's not sorry.
Okay, some is improved. Is it?
I don't think it's a limitation. So the way they had talked about it in this book, at least, was that TD0 is a prediction problem. So it's just trying to predict what is the next Q value you're going to get.
Okay.
But you're not actually using it for anything. Sarsa is actually, now you have to try to use the next Q value to improve your policy. That's what eventually you want to end up doing in the case, right?
And then how do you progress from Sarsa to Q learning?
you don't progress from Sarsa to Q-learning. Sarsa is one way to do it. Q-learning is kind of like another way to do it. Yeah.
And one big difference is that in Sarsa, you're always learning from the decision you make. So say I make the wrong decision, I'll backpropagate exactly that solution, which makes it on policy because we're learning from the things we do. Versus in Q-learning, it converges a bit faster because even if at some point, based on whatever policy, I make the wrong decision, I only update the weights based on what the best weights were. So even if I measure all of my states and I say, oh, this is the best one, but I'm actually going to go that way and see how that is. If I go there and I actually determines like that one actually was a bad decision, when I go and update, I won't update based on the decision I made. I'll update based on what the previous best was. So if this one is still the best way to go, I'll backpropagate that way.
Okay. And then how is that manifested in this formula?
That's the max.
The max, yeah.
So the way if you think about the way we are getting states, actions, rewards, next states, when you are sampling these, or when you have a database like the experience replay that you're getting them from, you are going to start at some state, apply an action, get a reward. So that's going to be your reward. That's going to be your STAT. But the actual value of Q that you're going to be inputting for update is not going to be based on that action that you've taken. It's going to be based on the best action you could have taken.
Okay.
Which is where the max term comes in, right? Just I don't see it in this expression.
Okay, so let's go back maybe a bit systematically. So this part we all understand, right? Do you have any questions? Harrison, you look like so lost. You good? Are you with us?
Yeah.
Werner, are you with us? All right, cool. Hurry up. All right. We catch up. You good?
I'm good, but I don't know because I see coffee cups here.
It's over there.
Yeah, use the
Oh, wow.
You can also,
So I guess,
get
as you're learning, is gamma kind of like something that is slowly being tuned and it's being optimized so that the estimated return or discount factor works the best for the entire network?
No, I don't think so. It's like a hyperparameter. You don't really tune that unless you're doing grid surfing.
So gamma, you found it at the beginning, and you said it, and you said it, right? All right.
Interesting, because I thought that gamma, the discount factor, was something that would have to be learned in the learning process.
No.
I don't know, but if you take some latest DeepMind paper, I'm pretty sure those folks play with it.
Well, that's like
meta.
But yeah, in a canonical thing, I think it's a hyperparameter.
All right, so we got that. I think this part is more or less clear, right? Temporal difference part. We'll good here?
I'm good.
All right. So in this case, I think this is what everyone just explained, right? So is there any comment we want to put here? Those W's, right? Essentially, and delta, I guess. So essentially, this is what we are updating.
Yes, and we are updating on every step. By default, right? Every step.
Yeah.
Oh, I just took a look. I think you're right. I think it is set, and then there's something called TD lambda where you have like a parameter that does what I was thinking, where it kind of controls like how much credit can be given to future states rewards, depending how distant they are.
Yeah, I think that one is a bit different, but that one is a bit hairy. Yeah, let's not go there yet. Maybe later. So this one is, I think we are clear here. Those weights. Okay.
It's worth noting that you adjust the gradient proportional to how high the current value is, which I find kind of interesting. in the last item there
Mhm.
is a multiplier saying that if the current value is really high, then I want more influence on my ability to learn. I just
Wait,
think that's
wait.
interesting.
Sorry, where's the
So the
symbol?
very last, so it's multiplying.
This.
That's not a
But that's the
Well, that's not a
gradient of
multiplier.
Q hat. That's the
That is
gradient
that
of Q hat.
that is the gradient.
Oh, okay, that makes more
So
sense.
gradient
Yeah,
of
I found that confusing. I'm like, why are they multiplying it by?
Oh no.
Thanks, thank you.
Alright, so what you're saying is multiplying by gradient.
Partial.
By gradient of.
I mean,
keep
that
learning at
part
state,
is
right?
no different from any other backpropagation. Like any other.
Yeah, I think if it throws anyone off, it's just because they're using the del operator from vector calculus there for the gradient.
All right. I think we're okay here. So essentially, in this case, is we are placing. Maybe I should take the picture from the video. Which one were we watching here a second ago? Not this one. This one, right? Yeah. Okay, after that, it's just logarithm. Okay.
If you want to see a working or like a semi-working example with code, you should definitely look at the textbook that was posted on the channel.
Why? You just posted something?
No, the deep reinforcement in action.
Oh.
Like that goes through it and it has code as well.
Okay. So I think with that part, we more or less clear. Q-learning. So should we describe whatever you were showing, or we just go to Q-learning? How does Q-learning work?
Okay. Does it make sense to go through Sarsa first, or it's not quite ready?
Okay.
You're saying Sarsa is one way of doing it and Q-learning is another way, so can we skip Sarsa?
Sarsa, I think, is the same thing as that's online learning. You wanna go over Sarsa?
Does it help you with, as long as it helps with understanding Q-learning? Otherwise.
Yeah, I wouldn't mind spending a couple minutes with Sarsa.
Okay. So we need to find the Sarsa.
Sarsa is for updating the policy.
Which lecture is that?
That's number 4. Go about a minute and minute 20 in. No, a little back more, minute 10, around there.
Is implicitly defined as an epsilon. Begin by initializing our parameters W arbitrarily. Our policy.
All right. So first thing to note is that TD0 and Sarsa is the same thing.
I'm confused. Why?
TD0 control is Sarsa. TD0 is the prediction part of it. That's why.
TD0 essentially is a one step ahead look. So essentially, TD0 means you only look ahead one step, and that's how you replace your value. TD is the whole family. There's a TD lambda, right? We're not gonna go to TD lambda, but let's say there was a TD2 or TD5, right? That means you care about 5 or 6 step ahead.
So lambda is for credit assignment.
Yeah, lambda. If it's
Okay.
TD lambda, is okay. How much you're gonna
Okay.
put an assignment for?
Okay.
But if it's to say TD5, that means I'm gonna look at the 5 step ahead, and this is how I'm gonna discount this whole thing. If it's TD0, that means you're only gonna look ahead just one step.
One step.
Is it one step, right? TD0 or just yeah?
Yeah, one step like R. So Q and then Q of S plus.
Yeah.
Or Q plus 1.
Why?
Lambda, there's no lambda. There's no lambda. TD lambda is kind of hairy. You also have to see how much you care about each one. That one is confusing. Like in TD lambda, I think it could be floating points, right? It does have to be an integer. Does it?
I've not looked enough into it.
Yeah, and you kind of adjust that lambda. I forget how it works. It's a bit weird. But essentially, TD0 is the same thing as SARSA, because SARSA stands for state action reward state action. Which
I see.
Yeah, which also means just one step ahead.
So I know we haven't got there yet, but I don't know. To me, like from what I've read, the TD lambda makes like a lot of intuitive sense, and I could see why you would use that. The TD0 seems like to me you'd kind of get. I feel like the TD lambda is always better performance, but maybe I'm wrong.
TD lambda is better, yes. You can earn better representation.
Like it makes more intuitive sense to me too. This like trace decay parameter where you just kind of have like a continuous value between 0 and 1, and you can learn like what the best amount to look into the future is. That makes a bit more sense to me. I don't know.
Yes, I think I recall this. So TD0 is the same thing as SARSA because you only do one step look ahead. Okay. But TD, let's say infinite, is the same thing as Monte Carlo. Because you look at all the steps ahead until the end of the episode.
Oh, okay. Sorry, I'm thinking of something else.
What's up? Talk to us.
Because are you still talking about TD lambda?
Oh no, we're not talking TD lambda.
Okay.
Let's not go there. It's too confusing. Let's just.
I finally realized what this is. It's just like instead of updating V, I update the key. That's what SARSA is.
We don't have to go to TD lambda, but you mentioned Monte Carlo, and I'm just kind of curious since I know a lot about like Monte Carlo sampling and integration techniques or like Markov chain Monte Carlo, but in reinforcement learning, like how do they do it? Because if you're like randomly sampling, that seems like you almost will never learn. You need a huge amount of computation power and time.
All right, so if you look back at this one, right? This one is Monte Carlo. In this case, G is the actual return. So if you are in this state and you take some action, right? So the value of this state is the value of that state plus this, no, not discounted. It's not discount, it's learning rate.
It's learning rate.
Yeah,
but the discount is implicit inside G.
Yeah, but the G essentially is this.
Right.
Discount rate of all the returns, right? So in this case is what you're gonna get. This step, first step, second step, third step, and all the way until the end.
Okay.
So in this case, this is called Monte Carlo.
I think one of the limitations for MC is that you have to compute offline. Like you have to go through the entire episode and you collect all these things, and then you can start updating with MC. Or with the samples you get.
But I'm sorry to sound stupid, but like what makes it like Monte Carlo? Is it randomly selecting the action at each state, or even as it like moves through the environment? Like what's Monte Carlo about it? Like random?
So as I understand it, we've actually skipped a lot of information that was in the book.
Mm-hmm.
The derivation for the Monte Carlo actually came from there's an expectation of an expected return, and the way that Monte Carlo is doing it is it's trying to do sampling and doing averaging in order to determine that expected value or the integral, whatever you want.
Yeah, that makes sense. Like a lot of the time in probability statistics, you have integral that you use Monte Carlo integration to calculate the expected value of. But I'm still kind of wondering if there's like some random choices that are being made.
So
go ahead. The random choices that are being made are the steps along the path that you're taking in your trajectory. So the different rewards you get at different times.
Oh, I see what you're saying. Yeah, when you compute the overall expected value. Yeah, okay, that makes a lot of sense.
I can think of like two. One is like just uniform random choosing action. The other is you have a categorical distribution and you just sample according to that categorical distribution.
I think Harriet wants to say.
Yeah, I just want to try to assimilate like there's Monte Carlo to sample this versus Monte Carlo to sample this test. But that like we say as stochastic because usually you will see some kind of probability distribution to get the random state, right? In this case, there's no like a distribution to
there is the distribution is the policy.
Yeah, so then
You sample from the
but there's
policy.
no Q here. There's only V.
What do you mean?
No, down you can have Monte Carlo on Qs, I think, too, right?
Yeah, but this one
is just happen to be V's, yeah. Because you can have a
okay,
algorithm.
Okay. You're saying if you're working on Q, then you have distribution.
What do you mean by
Wait,
distribution?
So Xian,
Yeah.
the returns that are getting, or the rewards that we're getting, how are we getting the rewards? You're applying actions.
Right.
You're applying actions based on some policy. You're starting them some state. You're taking steps, right?
But okay, so what is the policy?
Well, they don't say what the policy is here. Like that's something that you are at that given point in time, at that T, you have some policy, right?
This is how you learn it.
I think that's where policy is where, isn't that where the probability comes in? I'm just looking at the page. It's state cross action, and these are probability values. It's a probability matrix of state by action.
Yeah.
But these things, I thought these things don't really have a policy. The policy is usually just you pick the max based on Q, and plus some maybe exploration thing, like where occasionally the random.
That's the actions you're taking based on the policy. It could be like the maximum probability or something.
Okay. So if that's here, then okay.
Okay, Brian, did you answer your question?
No, I'm just reading some stuff right now.
My first guess then is the Monte Carlo part is you're sampling based on guessed actions or sequence of actions that gets you the discounted values. So that's first guess, and then the first guess would be you're definitely have the option of getting probabilities from the policy pi. Although it does, I'm just looking at Wikipedia. You don't have to have probabilistic policies, but I guess that seems to be the norm.
Okay, I think we kind of segued.
Yes,
I think we kind of got off track. Let's drop the TD lambda for sure for today. I think that one is a bit too hairy. Monte Carlo is I just remembered. So TD0 is the same thing as Sarsa. TD1 is the same thing as Monte Carlo.
Oh yeah, for lack, yes.
Yeah. Okay. So and the TD is essentially just temporal difference.
Mm-hmm.
So in this case, the Q learning, I'm assuming it's Sarsa, but with the Q values.
The big difference between on policy versus off.
Oh, I see. So that's the difference, right?
Yes.
Okay.
I
Okay.
think that he said earlier.
Okay. So Q learning.
Like were you staying on that policy or were you just going to?
Because with the update state, it does depend on what action you take, depends on which action the process does. So even if you do something different, you're still going to update your weights working the way you follow best, even if you know you're not making a decision.
Okay, I'm super.
On policy, make the wrong decision, you update the weights according to that. Even if you had a really good state, if you do the wrong thing, it might decrease the value of that state because.
So when do you update the policy?
You update the policy at the point where you take the max.
No, you're not updating policy here.
So it's up to you really. But after a certain, so like, okay,
Well,
what
the-
occurs is
the-
that you've got two different functions. No, okay, that was an extension of one difference. Let's figure that. They introduced that as taking paper.
Yeah. So let's first try to figure this part, right?
Okay.
So from what I see is you have two, I'm gonna call them Q functions, okay? So first is to pick policy, right? And second is the one you train. Yes? So what?
Second, first, what's first?
I think no, this is like a trick they did in paper, was to have two separate neural networks, separated, but straight up Q learning doesn't necessarily need that. You could be operating off one network.
Okay, so here let me see this is what I'm reading. Initialize W's, right? And you have some policy that you follow using this W, right? So you have some network. So you do greedy, epsilon greedy, querying this Q function that you have right now, following this policy. I mean, to come up with the policy. So repeat for many episodes. Initial state, blah, blah, blah. Choose action A from state S using this policy, right? Once you pick this policy, take action that this policy told you to take. So, and then observe new state and observe the reward that you're getting, taking the action from this policy.
Yeah.
Now, then update your weights based on the discounted or blah, 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 based on the reward that you observed, based on your current state in the according to that policy, and the best Q value from that policy.
Yes, except there's the alias change.
Yes.
Yeah, but this is that's the idea. You're taking the max Q, right? The max Q according to this action.
Yeah.
So it's not these action. You just take one the best. But after that, you just go to that state, and then you take the next action is not this action, but the one that follows using the same policy.
This is where it's confusing. I feel like the terminology, because S prime is the same in both cases, but it may not be the same in reality.
Wait, no, I think it is. Because when you took the action, you went to S prime, there's no way to reverse time and go back, right? You've done it, you've taken the action. The difference is you're determining the value of this new state based on things I could potentially do in this state, right? It's kind of like, bad analogy, but like imagine going to Disneyland. You could go on any of the rides. Wow, that's a great state to be in, but you don't have to. And the next step doesn't say that you actually do go on any of the rides. But you're saying that's a good state. I'm going to evaluate the value of my decision based on the state that I got into and the fact that I could do all these cool things, but I may actually not do them.
Mm-hmm.
I'm just using that as a measure of value. I may actually decide to go sit in the corner for the rest of the day. And then because that's what my policy is saying, right?
Yeah, exactly. That's exactly what I mean. So essentially, how can I draw this thing? You follow?
But we do update the policy, though.
Okay.
Oh yeah, that wasn't talking about update. I was talking about whether or not you the value
Are you sharing this now?
This new state to be
Yes.
is based on all the things that the best things you could do in this new state. But that doesn't mean that you're going to do them in the next step. It just means you take that into account when determining how to decide the value of the previous state.
You're just talking about the Q. That's all you're talking about.
Yeah, yes, the Q and the max A and all that.
Yeah. Okay.
Oh, wait a second. Go ahead, sorry.
There is a change of state?
Yes, there has to be. You take action.
Yeah, there is a
RS.
change of state.
There's no way you can prevent that. Imagine a robot. It takes an action, it goes to a new state. It can't say, well, I didn't do that. Because you did do that. you can't rewind it.
Can't you estimate what the reward would have been? Because you still have that effort with estimates Q values. So can't you assume that the reward would have been, so we're pretending we had made this decision, like we did make this decision over here, but then when we're updating the value of the state, we're not necessarily saying, copying this one backwards, we can still estimate the value of that state based on our current beliefs.
Potentially, but you don't know what the actions are going to be. One of the things that because there's no model here, you can't know what your action is going to cause the next state to be, and that's always going to be a big gap in your knowledge. Yeah. So you have to observe RNS. It could be that you just go off a cliff. You have no idea what's going to happen.
Okay, question. So as you update those W's, right? This thing, you update these weights in this Q function, or is it the separate Q function?
Yes,
that
that's that. Yeah.
The same one, right? So you only have one network.
You only have one network.
Then why is it called offline policy? Off policy learning.
Because the actual update of that Q is based on the max. It's not based on A lead or the other A.
I don't understand this.
So you could have taken that action based on that policy pi, right? The little A.
Yeah.
That could have been based on that policy pi that you had. but you didn't. You just went through all the actions you could take in the state as plan, and you chose what the best one would be.
I see.
That's a different policy that you were thinking about that at that point.
So where SARSA is the difference, you actually took that.
You actually did that policy file.
Okay. Can I have edit?
Oh, sorry. Good to have it.
We want insert some second.
No, how do I do that? Share.
So we can. You want anywhere to.
All right. So pick a policy using greedy. Right. This one, right? Then, well, how do I say it? We just copying the pseudocode, right? Let's just put the key points. Using the best.
Yeah,
the
best
best
possible actions are taken in that stage.
That's primary.
Can you see my screen?
Policy greedy or the best thing? We're still going to
greedy action, right?
I think what I'm going
So-
to assume that this is Q learning. not
So,
deep Q.
I'm trying to compare these two side by side.
Is why are they updating in situ? Why are they updating like as they're going along? Because in deep Q learning, that would break. That was the whole point of the paper is that if you updated your Q network while you were going through these actions, that would actually mess things up if you're using deep Q. But apparently for Q, that's fine.
All right. Could you please repeat that part? Let's make sure we're all on the same page.
So the two double, like if you look at the purple line,
Yeah.
the two W's in the middle, so S lowercase a, S prime lowercase a W, and then the one beside that, like the two saws, they're the same W, which implies that if you update the gradient of W, and if you update like the delta W over there, that means both of those are going to change.
Oh.
But there's only one Q network here.
Oh, you're saying.
Oh, I see.
Q and
Sorry, Q value, not Q
I
network.
see.
But for deep Q learning, if you try to do this, that actually breaks. That was the whole point of the paper, or one of the points of the paper, was that you can't update the same Q network. You have to have a target network and a network that you're working off of.
Is
that what made it better? Because I've seen other examples where they only have one network.
That was one of the things that made it better. Basically,
Okay.
what they were saying was if you change the same two networks, like if they're the same network, then you potentially have a cyclical loop, a feedback loop where it builds on itself and it causes instabilities. Because it's a neural network as opposed to this doesn't say neural network. No, it just says
I know.
whatever. It could be anything.
This is a table right now.
It's a table, really, yeah. So that we're getting confused here, but yeah.
Is it tables though?
Okay. Another one question. If you said, because you're batching the update in some fashion, right? That's the point of Q learning. DQN.
DQ learning, not Q learning.
DQN. So okay. Can you see my screen?
Yeah. Really quick. I think these are the network because we are updating weights.
I'm not convinced that that's the case because this is a deep, and I think this wouldn't work if you just want to. I'm not sure.
There is a lecture. There's a video that has deep in it, right?
Yeah. Okay.
All right.
So my point is, okay, maybe we'll have fun answering that video. If you set this T to 1, is that standard
What
Q
T?
learning?
Oh,
This T.
one.
That's basically my question. Then is it equivalent to Q learning? Oh, sorry. C, every C step reset it. If you set this C to 1, is that the same with Q?
I think so.
You think so? Okay.
Yeah, go on, what do you say?
Yeah, I think this is what you were saying, right? When you're actually fixing the network while you're learning.
Yeah.
It's like that donkey example. That's it, right? Like where you're trying to teach donkey to walk straight and you have
Yes.
a carrot ahead of.
Yes,
I see.
that's a good, yeah.
So you can't really train while you're updating it. So you gotta fix it, update your thing, and then as it's working, then update it.
got it. Okay.
So in this case, it's not that. It's not deep Q learning. It's just. But why we have W's?
It's a deep Q learning with the error replays.
Correct.
Where
So
they have not made that fix.
I guess we can say in progress.
Yeah, I want to read that the rest of that video.
Yeah, if you're talking, can you see my screen?
Yes,
that's on video 8, and then that's that far in, and it's just the W with the minus on top. That's where they're fixing. That's the notation he uses for fixing the weights, the periodic fixing of weights.
Which lecture is that number?
That's number 8.
Let me pull up and I can copy it real quick. Give me a second.
Yeah, 3 minutes 27 seconds.
8, right?
Yeah.
Uh, 3 minutes and what?
27. Or thereabouts.
Wait, you just skipped the donkey thing.
Are you on donkey? You want to watch the whole thing?
No, just the donkey.
Just a donkey. Okay. Yeah, might as well watch the whole thing.
Consecutive experience tuples. There is another kind of correlation that Q learning is susceptible to. Q learning is a form of temporal difference, or TD learning, right? Here, R plus gamma times the maximum possible value from the next state is called the TD target. And our goal is to reduce the difference between this target and the currently predicted Q value. This difference is the TD error. Now, the TD target here is supposed to be a replacement for the true value function Q pi SA, which is unknown to us. We originally used Q pi to define a squared error loss and differentiated that with respect to W to get our gradient descent update rule. Now, Q pi is not dependent on our function approximation or its parameters, thus resulting in a simple derivative and update rule. But our TD target is dependent on these parameters, which means simply replacing the true value function Q pi with a target like this is mathematically incorrect. We can get away with it in practice because every update results in a small change to the parameters, which is generally in the right direction. If we set alpha equals 1 and leap towards the target, then we'd likely overshoot and land in the wrong place. Also, this is less of a concern when we use a lookup table or dictionary, since Q values are stored separately for each state action pair. But it can affect learning significantly when we use function approximation, where all the Q values are intrinsically tied together through the function parameters. You may be thinking, doesn't experience replay take care of this problem? Well, it addresses a similar but slightly different issue. There we broke the correlation effects between consecutive experience tuples by sampling them randomly out of order. Here the correlation is between the target and the parameters we are changing. This is like chasing a moving target, literally. In fact, it's worse. It's like trying to train a donkey to walk straight by sitting on it and dangling a carrot in front. Yes, the donkey might step forward and the carrot usually gets further away, always staying a little out of reach. But contrary to popular belief, this doesn't quite work as you would expect. The carrot is much more likely to bounce around randomly, throwing the donkey off with every jerky step. Each action affects the next position of the target in a very complicated and unpredictable manner. You shouldn't be surprised if the donkey gets frustrated jumping around the spot and gives up. Instead, you should get off the donkey, stand in one place and dangle the carrot from there. Once the donkey reaches that spot, move a few steps ahead, dangle another carrot, and repeat. What you're essentially doing is decoupling the target's position from the donkey's actions, giving it a more stable learning environment. We can do pretty much the same thing in Q learning by fixing the function parameters used to generate our target. The fixed parameters, indicated by a W minus, are basically a copy of W that we don't change during the learning step. In practice, we copy W into W minus, use it to generate targets while changing W for a certain number of learning steps. Then we update W minus with the latest W, again learn for a number of steps, and so on. This decouples the target from the parameters, makes the learning algorithm much more stable and less likely to diverge or fall into oscillations.
Okay. Go ahead.
Carrot, right? It's just that, like you say, the one step or a few steps ahead thing. But that's like information that you already know, like some of the steps beforehand. But wouldn't like that thing there? Is it a random variable? So is it deterministic? Which means that you have information of the future. But then that thing like will not change, like you said, when you actually get to that state.
Okay, so I think in that case, the carrot was just to show you the decoupling part. So the idea is you don't want to train a donkey as you are on the donkey.
What you're saying is, yes, I understand what you mean by deterministic. It isn't deterministic because
It isn't.
no, because just like with a donkey, the position of the donkey is based on both like the rod and also which way the donkey is, like where the donkey is, right? Because you're on the donkey at the same time. So the problem is maybe a better. So are you confused? What's the question?
I mean, like per se, it's like because okay, so per se you're at this stage, right? And then you are making decisions by having the information of a few options before you, right? And then, but I mean, like at this stage, at this time, and when this information are like that. But how do you know that when you actually are not there, it's not changing? You know, like is it like a random variable?
It's not a random variable. It's more like so. Let's say I'm trying in Toronto. Let's say I'm trying to go towards the CN Tower. I will take some steps in some directions and maybe stumble a bit, but the CN Tower is going to be always where it is, right? Like the CN Tower doesn't move, so it's deterministic in that sense, right?
So in this case, so because okay, so per se, my path, I think it's a stochastic process, right? It's a random variable that I take.
Yeah.
But then, so there's another variable which indicates that carrot, which is the reward, right? And in that thing, in this case, you mean that it's not a time series. It's not a stochastic constant, but it's actually a constant variable at each. You know what I mean? It's like, so it's, right? So my state is a ST. It's a series. It's a sequence. But then that thing is actually
the carrot is not a target. So if you're writing, like, I think analogy is missing a part where there's actual some target you want to go to. That part is deterministic. And then what he's saying is, okay, in theory, I just point my carrot to that direction, and then donkey should move that.
Right?
But no, but the thing is, if I do that, the carrot is not stable, and the instability is also caused by the movement of donkey itself. So you intend to point that way, but your carrot could be like be swung to that way, because of the movement of donkey itself. So the donkey could actually go that way. But you do have a target in mind. That is a target.
Because one of the biggest problems with RL, the reason we invented RL in the first place, as opposed to just using basic neural networks, is that there's too many steps between where you are now and when you know that you've done the right thing, right? And you don't know, then maybe you know, right? And because of that,
say we use like a variable to like simulate, to model it, right? Like you're saying, so my
Harriet,
my situation is ST, right?
can we do the same thing so other guys can see it? Give us just a second.
You want to write on that board?
It doesn't really matter. Yeah, give me a second.
t, right? So for say my action at this stage is actually a function of having the information of this caret at t+1, right? Then I make, and then maybe some other variable, some other factors too. My question is,
the state is a function of the caret at t+1.
So this is like the donkey, right? At this state at t. And then what I am going to do at t, my movement, my action depends on the caret that I know at t+1, right? Like a previous, like a one step ahead of me, right?
Yes. So in this case, maybe to make it less confusing, this is actually delta value of st. It's more like, because it's not your state that's changing. This is what's confusing is, in this case, the donkey doesn't represent where you are in the action space. It represents what the set of weights are. In other words, the neural network. So like S can be a little confusing here. Does that make sense?
No, I wanna know. So I wanna know my at t, the decision I make. What variable I should use?
When you say decision you make, do you mean
like for say
A,
right? Okay. So let's say this is the A. So at time t, my action here depend on the caret at t+1, right? Like my information I know at t about t+1, right?
I think we're confusing
or what I
here.
think it is.
Or what I think it is.
Yeah, exactly.
Yeah, but anyway, so it's like the current information available to me at this moment about t+1, right? My question is, so is this as t+1, right?
Wait, usually at+1 equals to ft.
It's a function. It's like, so because this thing actually affects my AT,
so
right?
AT+1.
I think it's the action taken at time t though, right? So AT.
Actually, and then what is C?
C is like the situation I think that is going to happen at t+1, right?
I think you're really going out. That caret is really just an example. So can I?
I think we're confusing two different things here.
It's not.
One of them is what actions do you take, and the other one is how do you update the network. And those are two separate things, and I think we're confusing them.
So
the way that's written is like not causal, because you can't know it. You can only have prediction.
Assume, I assume.
You can't. You have to try the path before you can know it.
Yeah, raise.
So okay, here's the confusion, right? Let's forget the card for a second, right?
Okay.
So you have this Q network, right?
Yeah.
And this thing today with that algorithm,
yeah,
it keeps being updated with every step, right? And as you update, you find your policy based on the same Q. And that's confusing. It's really hard to converge. So what they say is have a copy of Q, right? You have this Q with the weights W minus. And you have this Q, right? So with every step,
Q is like already like a whole episode, right?
Q is a network.
A function. Okay.
Yeah.
Okay.
Q is a neural network.
Okay.
Yeah, it's a neural network. I'm gonna draw this little thing here. Okay.
Cool.
Right. Anyway, so the idea is with every step, you update this guy. With every step, right? But this guy is fixed. And you fix this one, you pick policy actions from here. This is the policy, right? You pick your policy, you pick the policy and the actions from this queue, which is fixed. But this guy keeps updating with every step. So that's the idea. With the caret, essentially.
What information is contained in this queue?
Wait.
No, like
it's like our caret. It's how much value we think is down each path of actions.
The way I think about it,
it's like our best guess at all the different rewards given our actions.
Okay, it's so basically that the output of this is actually a set of variables to a time t, or like a situation, environment, or
So,
like what the assumption.
I think given like you have like two different actions, it would be two variables, and it's the future rewards given action 1 versus action 2.
Yeah, exactly.
Okay.
So
Oh,
given your
okay.
state, currently you have any number of actions you can take. Q tells you what the values of those options are. I do this, this is how
The
good it is.
rules, so it's a set of rules.
No, more like a set of what I'm going to get out of it.
Okay.
Like how good is this for me if I take this action? It's like you're at a buffet. If you eat this food, it's really good. If you eat this food, not as good. That
So
kind of
like
thing.
the utility function.
Yeah,
Okay.
that's a good way to think about it. Yeah.
Okay. Okay, great. Cool. And then, okay, so you say that this actually updates at every stage.
Yeah, so every time you make a step, you update this queue, right? Okay. Yeah. And then once every C steps, you just copy this guy here, right? And then you keep making. Okay, you make a step, and then you chose the step based on this queue, which
So
is
it's,
fixed.
It's Markov, one step only.
Don't worry about Markov. Like right now, this concept is with the fixed weights, right? So when they say the carrot, right? Essentially, this fixed policy is where you're standing, where you're holding your carrot.
Okay.
And this queue is essentially when you're learning is where you're moving, how you're updating. And once you learned a little bit, and once your queue function is, I don't know, converged somewhere at some state, not the file, but somewhere improved, you copy this guy.
So this thing actually.
Yeah. So the idea essentially is you're not updating your queue as you're learning. Maybe it could be down, but maybe it's unstable. I don't know. Essentially,
Otherwise, you end up chasing your tail potentially. It's almost like you're chasing someone down the street. The fact that you're chasing them means they take different paths. So you can't, it's not predictable where the person's going to go because you are affecting where they're going to go.
So then when this thing converges, then does it become what Xian said about the deterministic target then?
No, you always have a target.
Huh?
You always have a target that is decided by the environment.
I think you're missing the Q function. What Q is?
Okay.
Yeah.
Q is within the agent, but
like the quality.
R part, everything else, those parts. In this case, you can see it as deterministic because they are provided by the environment. Those things are set. Those things are the guidance for.
I think this helps. This help understand. Oh, this two combine together works.
Click.
Great.
Yeah. Good.
Yeah. Thanks.
I think you're also making an interesting point about determinism, which is maybe just worth mentioning. Which is like, even though our reward may be an estimate, like say I've got a cup I can look under, and maybe there's a coin with 50% probability. The reward of looking at that is not necessarily deterministic, right? Because depending, one time I look, there's a coin. Next time I look, there's not. Next time I look, there's not.
That's true too, and especially in a dynamic system.
Especially in a dynamic system or a game, maybe they're going to return the shot, maybe they won't. This does its best job to estimate kind of the probability of getting a reward as well. So it's not necessarily going to converge to the actual reward. It's going to be proportional to like how likely is it I'll get a reward down this path as well.
I think to elaborate on that point, if I understand right, that would depend on the underlying.
Page, you have questions? No,
I was just looking at my computer.
Oh yeah, can anybody hear me?
I'm going to turn volume off again.
Yeah, we can
somebody
hear
else
you.
want to turn volume on in a sec?
Yeah, okay, I guess those guys can.
Yeah, I don't think our volume is loud enough.
Yeah. Hey, yo, can you guys hear us?
Yeah.
Yeah.
Were you muted?
I don't think so. I don't know.
No, we weren't. It was just, I think our volume wasn't loud enough before. I don't know.
Yeah, I guess so. I think because we were going through Yervant's, and I guess maybe his audio was low or what. Maybe.
Yeah.
Okay. And I think the only thing, if I understand right, I'd want to clarify when we talk about fixing the weights in terms of that evaluation step, and that you're keeping a fixed set of weights for a few iterations, that's not actually the Q learning. That was just an improvement, one of the tweaks that they did to Q learning because of that issue, what we were just all talking about.
Yes, so it's very last step essentially, this learning part. I think this final equation is a bit convoluted. it's like two derivation of the Q-learning. First is based on the dreams, based on the sampling. So it learns based on samples, and second based on the fact that they fix weights.
Yeah.
So it's a bit like
There's a lot of things going on at the same time. Yeah, I find that to be the worst part, the most confusing part of this.
yeah. But yeah, the one that we were talking about right now is this part essentially. So let's ignore that part. Set target. Anyway, update Q based on these functions, and then every C steps we set your Q-learning. Did I answer your question or did I confuse you? I think I might have got off. William.
Oh, me? No. I think, yeah, no, it sounds like, yeah, sure. I think we're on the same page.
Yeah. So the only other thing that I think we need to really nail is the sampling part. That part is a bit easier, but do you guys understand that part?
Yeah.
Thomas, Ala, do you have any questions with the sampling?
No, okay.
Go ahead.
Sampling is the experience replay, right?
Yeah.
So I know in the video they said the instability kind of already solved by experience replay, but then kind of the target network is solving another problem. I just don't see how the two are solving different problems. I feel like they're just solving the same instability problem. Because in experience replay, because you're doing online learning, so it's unstable, right? So that's why we do like experience replay to make it more stable. But target network is kind of doing the same thing. Like it's also solving the instability issue.
I think at least one difference is they do, when they replay, they don't do from start to finish. There's some random shuffling going on. So random shuffling effectively prevents you from getting stuck into some kind of local minima.
Okay.
Is that local minima? It's just like getting in a weird situation where you think, okay, this is a special case, but if I always keep doing this, like I'll get the best results, and then you generalize into broader situation and then fail miserably. So I think experience replay at least takes care of that part. So it's there's a difference.
So I see the methods are different, but I don't see how the problem they're solving is different.
I think they're kind of complementary in a way.
Yeah.
I agree with you.
Partly because with one,
so with one cannot really solve the whole issue.
Yeah.
Okay.
And I agree with you that they are generally solving similar things, but they are both needed.
But in the video says it's not really. You know, in the video it says no, kind of it's a different issue. But I just don't see how it's. But anyway.
So again, say assume that you don't have experience replay, then you have that problem.
Yeah.
I had like, so the solution is, okay, I have to go randomly into like different states to maximize my chance. Then how do I do it? I can't just do it with what is the thing called? Fixed Q.
Yeah.
Method. That is why it's not enough. I need randomness. So in order to have randomness, I need to have a buffer of history. In order to have a buffer of history.
Okay.
That's at least that's one purpose. But yeah, I think they probably solving the same thing.
Okay.
No, that's a good point. You had a question? You had a comment? So yeah, I think we are more or less on the same page here then. So this algorithm now makes sense, I guess. Did you have like a better version of this?
I already posted it.
It was here, right?
I'm not sure it's better.
With experience replay.
It's more academic. Yeah, where's the experience replay from?
How do you do?
The D. Yeah, the first one.
Yeah, I don't need in the middle, like right above that big bracket, sample random feedback transitions, or store transition sample.
This?
Yeah, right there, right there.
I see.
The experience replay.
Sample feedback transitions. Okay.
Okay, let's go line by line and make sure we understand every single line. So initialize memory. This is our replay memory, the buffer. Initialize action value queue with random weights at the very beginning. Okay. Initialize target action. So we're just copying it, right?
We're just making a copy.
We're just making a copy of our queue network. What?
The first is totally random.
Yes, it's super random. So for episode up to M, I'm not sure what M is.
M is like the point of you're getting really impatient and don't want to.
All right. Initialize sequence S is equal x1 and pre-process sequence. Okay.
Initialize sequence S. Wait, S is a sequence?
I guess in this case it's like frames. Remember, like if you want to have 4 frames, yeah.
Okay.
Yeah.
What is? I didn't understand why it's the 5.
It's a feature transformation. Remember?
Phi is
Oh,
You're just
you
reducing the number of
transform.
pixels.
Oh, you transform the states into a
reducing number. I think as well as the color. Put on color to the 2 things. Yeah.
Yeah.
So it's no network digestible. Otherwise, the space blows up. Something like that.
Okay. So then for T is equal to T. All right. So we're picking the action from our queue network. Yeah, this is upsell ingredient essentially. Right?
Yeah, that's absolutely.
Wait, what?
So one is like
What is the
explore
epsilon?
versus exploit. So maybe we'll choose just a random action.
That.
Otherwise,
I was
we'll choose that.
Yeah. So this is the epsilon greedy part. Okay.
Okay.
Execute action and observe reward and the next image. So which is in our case it was a state, next state.
That's T-1.
Is the X wrong? Should that be S?
Where? This?
No, wait, no.
X is the kind of raw input,
Okay.
and S is the one when you go through phi to pre-process.
X is the raw input.
Yeah, I think so.
X is the image, and S is
sequence.
S is the processed image. Oh, sorry. Oh, yeah. S is. Yeah. Oh, yeah. S is 4 frame image.
4 images.
Yeah, 4
Which
images.
is a sequence
Okay,
essentially.
yeah.
So once we observe the new image and the
yeah.
reward, we reset our sequence, right? By adding that S, A, and X1. Interesting, right? Like in this case, we're actually including action as well.
Oh.
Yeah, this is really interesting.
Okay.
Include the action.
Yeah, it's not just.
Next state is going to be the next set of 4 is going to have the previous set of 4
with actions.
Action and.
So the neural network has an input for actions.
I feel like we won't understand this until we look at the code.
All right.
Yeah, good point.
And then we pre-process. We just pass it through our function, right? Then store transition in memory. It's interesting because this phi is phi, right? How do you say it?
Phi.
Yeah, it's phi.
Phi is also learnable.
Yeah, this phi also already has A in it, but and state. So you kind of have it twice. So you kind of have it twice. I don't know.
Wait.
Partly because it's not necessarily depending on action, I'm not always going to get the same result, even in the current state.
Okay.
What?
Because it could be random variables in the game. For example, a tracker thing requires move randomly. Even if I like go into an empty space, it's not always going to stay empty. There's a chance that the next card can move into my lane. So it's important to store not just the current state and the action, but also the next state as well. What state, how did the state evolve?
Okay. Wait, but what is phi again? Phi is the
feature transformation.
Transform state, compressed state, like a transformed representation.
So we covered it.
Yeah.
This is like the grayscale and stuff.
We don't have
this one.
I thought phi is a function, but okay.
Yeah,
Phi
this
is
part.
x. Phi is x.
Phi is the result of the function as well.
Okay.
Phi is a function.
Okay. Yeah.
Phi is basically a simplified version of S, right?
Yeah.
Yeah. Okay. Okay.
Is it simplified? I think it's just processed.
Yeah, well,
Simplified.
plus,
Simplified.
like, make it
It's
more
scaled.
editable for the
Yeah,
Simplified.
exactly.
Scaled down. Scaled down.
All right, so just one comment is that we actually have in our memory we store phi, a, r, and phi plus 1, right? But this phi inside already has s and a, so we store s and a twice in our memory.
Well,
We store a twice in our memory.
Okay, this is how we need to look at code.
Well, it's not stored. It's stored in a transform form and in raw form. But you're right. Yeah, basically, you're saying is it's somewhere in there twice.
Yeah.
Yeah. It seems to me that SAT going into S implies that your action is considered part of the state. For example, let's say you're driving and you hit the gas.
Go
now
to
you're here. Now you're here. The fact that you had hit the gas in the previous action matters as to what you can do next. You can't just turn the wheel in a like if you were steady in that spot versus if you had just moved into that spot quickly matters. Does that make sense? Like what your actions were. That's what the implication is here.
All right, so what you're saying is you want to store not only two states, but also how you got into that state, right?
What you did to get into that state. It seems like they think that's important. I'm not convinced, but apparently that's what they think.
So I guess in the world you can get into the same state maybe by running or by biking, for example.
Yeah.
Yeah, it kind of makes sense. Yeah, maybe you got from one state to another with the same speed, like by running or by driving.
Yeah.
Different actions.
And some actions you can't take if you took a previous action one way versus another.
Yeah, and it kind of matters. Okay, I buy that.
I only semi-buy it, but yeah.
Makes sense.
Makes
though.
sense.
Yeah, it makes sense.
There is a section on page 6. 6, I think.
6
under algorithm.
Under algorithm. Left, right, which side?
Right side.
Oh, there you
Yeah.
go.
So they talk about the task being partially observed, and many states are perceptually.
Where is that?
Yeah, where's that?
That paragraph. You're right. You're looking
Because
at it
the
right there.
agents only
Here?
observe the current string.
Yeah.
Uh-huh.
That's why they seem to be storing actions for states.
But that explains why you need 4 frames, but it doesn't explain why you need action as well.
Is it not?
Okay. Yeah.
I like
Does
the.
it not? I don't know.
Because it's basically saying if you take a still screen, you don't know much what's going on.
Yeah, but
So it's saying.
actions are going to happen during that between the 4 screens, right?
Yeah.
Sequence
of
you have
actions.
that agent like at the bottom, like no, maybe it's doing something, but the ball is already up there, so it doesn't matter what the guy is doing. I kind of buy our argument, like.
Your side makes sense.
Yeah.
But intuitively, it kind of makes sense to me because if you think about it as like you're playing Pong, right, which is one of the applications. So if you are playing Pong, like you can go up or down, and if you were going up, wouldn't that affect what you are going to do next? You will last.
That depends on whether the 4th frame can encapsulate that, encode that information. Maybe yes, no.
You know what? Actually, it actually makes sense, right? Let's say the ball is coming pretty close to you, right?
Mm-hmm.
In that case, it actually matters where you were. So you want to kind of preserve, like,
Because it
were
also
you
matters
moving
where
closer
you
to the
hit
ball?
with this ball, right?
Yeah.
So I guess that kind of can capture those situations where you would want to hit the ball like from the tip of the paddle instead of the middle.
Right.
I'm not sure. Does that make sense?
Yes, it does.
Like intuitively in my mind it makes sense. But
I can't think of a case. I agree with you. I just can't think of a case where your action would give more information that 4 frames would not. Whereas if it's moving, yeah, that's like even in like Street Fighter type video games, it matters what action you take now because that affects the combo that you have later. But you can also see that in the visual of the video game. So I don't know why that's.
Here, can I just jump in here? Bilal is just saying in the comments he doesn't have audio, so he's just saying storing the action and transition is the whole purpose of experience replay. Which actions leads to which state from the starting state. So this, because we're dealing with the experience replay, you're not actually dealing with the environment in reality, and so that's why you need to have the. If I understand Bilal right, that's why you need to have the action information stored as well.
Which is true, and we get that. The question is why state ST+1 also includes action, is a concatenation of the previous state, the action, and the new image. It's not the D part. That's like the line.
I think that's notational, unfortunate notational decision because we know the states are very specifically defined.
This is one version I pulled what they did with Keras. So it's pretty straightforward just as simple as okay, these are the 4 frame input, and you have another input, which is the actions input. And then how do you combine the two? You at some point combine the two. Oh yeah, layers merge. You merge it at the very end almost.
How does that happen?
So you have 2 parts as input. One is the frames, the other is actions.
Yeah, but how?
And frames goes through conv nets, like standard conv nets. And then in here you have if frames goes through conv net and all the way to the end, maybe you have some fully connected, and on the other hand, you just connect those actions into the final layers.
Oh.
At least that's what it looks to me. What it looks to me like, because action inputs are filtered output, are concatenated. Oh, merge is multiply. So you multiply that with the output with your actions. Okay. Finally, we multiply so actions is being used as some kind of mask in a sense. You only multiply the actions at the very end with the output you get. Really? Now I kind of remember seeing it somewhere in the paper actually. I think someone mentioned it.
What did they say in the TDLS talk?
I remember something that I remember Nick mentioning that. But I don't remember. But this is exactly what this implementation is doing.
Yeah, no, I retract what I said. Though I get what you guys are saying.
But okay, we move on.
All right, let's just move on then.
We'll figure it out at home and then tell us.
Yes.
All right, so.
Well, I feel like it's kind of important for deep traffic too.
Yeah, you do need the whole tuple.
I guess the point is it actually effectively incorporates the action from the previous step. In your network, it actually is taking into account the actions.
Say it again?
It's actually taking into account the actions when you are trying to compute the queue.
Okay, yeah. So we store in the memory sample random mini batch of these guys from D. So when they say mini batch, essentially it's like multiple of them, right? Multiple sequences of from the experience, but do they have to be sequential or you just pick them randomly?
You pick them randomly.
Randomly? Yeah. So something that happened today, something that happened yesterday, something that happened.
I think the randomness is important. You remember that tennis video you saw?
Yeah.
I think that's essentially what it is.
But in that tennis video, right, when you remember that, you wanna recall the whole process, right, of swinging and stuff.
No.
So you have a very long battle where involves balls keep coming this way.
Yeah.
So you are very biased towards I should use this technique in particular. That's without randomness.
Yeah.
But if you have an entire history, then you go from some other places where coming from here it could happen. Then you get a more holistic strategy. Am I making sense?
Yeah, I agree with you. It's a bit more scientific. It's a little counterintuitive in my opinion because you're not really considering entire chains of actions. You're just kind of like spottily picking bits of transition, which is not really how we do it with our own brains, so far as I know. You're like, is that what you're asking?
Yeah, the way I see it is, if you go back to that example with the frames, with the videos, if you pick the random, it's just going to be like 4 frames at a time, right? So that's how you see.
Yeah.
That seems like
so in theory, that 4 frames should encapsulate the entire state. Like the entire state, like you go to any point in time. If you just take those 4 frames, and it should tell you the entire situation. You should just you can be parachuted into that situation right away, and you can start playing over there.
So when you replay that one memory, right? Okay, so let's say I'm replaying that one memory with 4 frames, right? And those, I'm assuming those actions are kind of embedded in those 4 frames, right?
Yeah.
Each frame of my memory has a sequence of frame action, frame action, frame action, frame action, right?
Probably.
And when I take that memory and I embed it into my new key learning network, I should get new set of rewards, right?
So you're not
Yeah. Sorry. So do you get one reward for the frame or for the 4 frames?
That's my question. So if I take, okay, I was in this state, took this action, got into this state, got this action, blah, blah, blah. All this happened. 4 frames and 4 actions. So do I recompute my rewards throughout all those 4 steps?
But the reward is something you store. It's not something you compute.
I don't think we're storing all the frame action, frame action, frame action. I think in PyT there is 4 frames.
Which one? PyT?
In any given PyT,
Okay.
it
Yeah.
contains the previous 4 frames, and then the action we took as of that last sentence.
So really, it's 2 frames per se, like 5
yeah.
and 5 equals 1.
Okay.
Yeah. So like 5 plus 1 would be
Oh.
the previous 3 frames plus the current frame.
Okay, makes sense.
I see.
Makes
So
sense.
so this reward is coming from the memory as well, or do I actually observe this reward when I replay in my memory? It's in memory.
Yes, it's like you're going at night. You're going over all the things you did during the day, and just like
You remember the reward you got, so it is really the reward, but it's the reward you remember.
Oh, reward that I remembered. I see. I
You
see.
got it, and then you're gonna save it for later and be like, oh, yeah, pick that up. Oh, good.
most of those R's are going to be 0 probably.
I see. So in this case, I set my Y to RJ. How do I do that?
It's just a terminating. So there's if your episode ends, then you can't have expert.
Okay, what is Y again?
Why is a target?
Yeah.
Target?
How you can do loss.
Right. So you want to calculate the difference between 2 things in order to do a back propagation, the gradient propagation. So why I incorporates the actual reward you receive from the memory, or receive from the environment. So that's kind of like your target.
It's just that temporal difference formula. You just like
Right.
the Y, and then you
Okay, so I'm pulling this is for my memory, okay?
Right.
So this gives me state, action, reward, state. So I plug my state here. I take this action, I guess. No, I'm not taking this action. I'm
No.
taking the best action that I should have taken.
So this, notice how there's T, lowercase t up there, and then this is now J. We've completely changed the subscript, right?
Yeah.
So these J's have nothing to do with where you currently are. They're just history.
Right.
Yeah, so okay. I don't know if that was clear.
Yeah, so, but I'm updating my actual queue, right?
Yeah.
I'm updating my actual queue table. I mean, queue network in this case. and I just want to see how I'm updating it based on my memory. So I see how I fixed my weights, right? This is my weights are fixed. I see that from memory I got my new state where I transitioned, right? And then I'm taking the best action from that stage, right? And this is the reward that I observed from my memory, right? Oh, I see. And then this is essentially my new reward, the new Q value
Yeah. So
for that state.
Yeah. Back to this guy here.
Yeah. So based on that, I call this is my loss essentially.
Yes.
With respect to the parameters of Q that I currently have. Okay, and then do I update that? Or do I update my Qs?
You have one thing stored, and here you keep updating your
Yep.
stuff in here, and periodically you have this thing, like you replace this with your new thing.
Well, where is it showing that I'm updating my Q values?
Perform a gradient descent step down.
Oh, I
Variable
see,
in
I
here.
see, I see. Step on this with respect to the
to the
network
network
parameters.
parameters.
I see. And then every C steps, you just copy that the whole network. Okay.
I feel like maybe by the end of this time or next time, if you guys are down, we should maybe write out this pseudocode, but just like in plain English, so we can actually logically follow and build an intuition of what's going on.
Can we go straight to the PyTorch?
Honestly, maybe we should.
Yeah.
Yeah.
It's just a lot of steps, and it's kind of hard in the pseudocode to keep track of everything the way they've added also the math notation.
Yeah.
So you all should have access to the. Try to go over it again and maybe write in the plain English like I was trying to do meanwhile. Here.
Sorry, you cut out there for a sec. What were you saying?
Yes. So you all have access to this document, DeepQ Learning.
Okay.
So try to add comments. Maybe next time we meet, we just go over those comments. Try to add comments just for this algorithm. I think that's the only thing we really have to understand.
Okay. Can you scroll down to actually this version?
This?
I just want to make a comment. Okay. So is it true that?
Sorry about that.
No worries. See you later.
So is it true that this is sort of like this is a very kind of intense thing that like you're in a battle, basically you're playing, but what it is actually doing is I play a little bit, and quickly on the spot I started reflecting. I take a very, very small rest. I start reflecting, update my strategy, then I keep playing the same game. So the point of this is that I think they actually mentioned in TLS is basically you so that you don't have to I failed at like throughout the episode and have to restart the episode. That wastes a lot of time. So I quickly update on the spot, and I sample from a previous and I quickly update a little bit, and this entire thing is kind of real time. So that learn episode, I think my understanding is that it updates very rapidly. Like only update a few steps, learn, update a few steps, learn, and this entire thing is like you can keep doing this like for hours and hours long. So there's no period of playing and training, and playing training is like a train bit play, train bit like it goes through the whole thing. I think they did this to speed up the training process because like they this could keep going for like I don't know 24 hours and 40 hours.
So you mean to say capacity M is pretty small?
Capacity of what?
The replay memory is small?
It's not necessarily small. The replay memory could be, if you have huge memory, you can store as much as you want.
Okay, so
but
what was your point then?
you update yourself throughout the play. It's not like you play an episode, you update it. You play episode, update, like it's being updated online incrementally, little by little.
Makes sense, yeah. Okay, so we have about 9 minutes to answer all the questions that we have and add any comments. Do you guys have any questions?
So we do traffic thing.
Sorry, what?
I just have to review everything.
Yeah, the condense. Sorry, what was that?
Are we gonna do deep traffic next, or?
Yeah, let's jump into code next time.
But deep traffic.
If I understand, it's not actually.
It doesn't really have much to do with this.
Yeah,
That's the problem.
we can just build like a game. And solve many examples. It seems pretty easy.
Why is it not code? It's like code in JavaScript. Right?
But have you seen it?
Are you guys? What do you guys think of the PyTorch example that Jian gave? You want to do that one?
Okay. Wait. Okay. My understanding is the deep traffic. What are you getting to is basically you're going to be using JavaScript, and I think the standard, like you're using JavaScript and with a framework made by Andrew Karpathy. That hasn't been updated for like, I don't know, 3 years or something. But you use that, you can build basic like neural networks. But I think what you'll be doing for the most part is actually tuning a lot of hyperparameters. Those are actually interesting things you can look at, because like for that particular problem, there's like, I forgot those parameters, but it's heavily related to that specific deep traffic problem. So I think that's you'll be spending most of your time on is actually the parameters and things. The other thing is I saw a lot of deep learning repository. They're actually not playing Atari. They're playing CardPool.
Yeah, on the PyTorch website, you posted about the DQN tutorial, and it is CardPool.
The CardPool, and the third thing is the thing I just showed. That's actually Atari.
Oh, okay.
So I think we have options.
So
decisions we need to make.
What do you guys want to do, Atari or CardPool,
or deep traffic?
There's one big concern in Atari, and that is it's going to take a lot of processing power. And when you like Amazon Web Services, it on laptops.
Okay.
Versus something like the Pool or like the Stillwater game. I think they give you parameters. You don't have to do so maybe that's just something to weigh there is like how much process power we need for it.
Right.
Maybe Atari is pretty big one.
Right. Okay. So we're gonna go with the gym.
But can we do anything that's not CardPool?
Yeah. There's Brick World.
Yes.
You can do it too. Just try to say other ones you can get.
There are many games like I saw so many.
Do you guys have any comments online?
I'm down for and going through anything, but I don't really know any JavaScript. So if Zing wants to go through that, he needs to, I guess, maybe help me through that or just screen share. I'd like to see some of the hyperparameter tuning though.
You know, to be fair, the guy who recommended the deep traffic, is he here? Someone proposed deep traffic and never showed up. So I guess we can switch and we'll be fine. So
well, there are a couple of options as well.
yeah, there are like other options, like whatever you guys feel like. I think this deep Q learning is very interesting. So if we can actually implement it, that would be pretty decent.
Which one had PyTorch? Because I prefer to stay with PyTorch, to be honest.
Both CardPool and I think, yeah. Like there's PyTorch implementation in DQN for sure. That's just generally speaking.
And what was the deep traffic paper? What were they using?
That's JavaScript.